Welcome back to Statistics. I'm Dr. Jeff Groh. Today, we're going to continue our lecture on linear regression, and in particular, we'll talk about prediction intervals and also about variation. Remember, a confidence interval is a range of values used to estimate a parameter. A prediction interval is a range of values used to estimate a variable. So confidence intervals were to estimate parameters for the population. Prediction intervals are used to estimate some variable. The classic example for us will be in these intervals that we will use to estimate the value of a variable. We'll have some confidence level on the values within that range. We will find that the farther away they are from the mean of the data, the wider those prediction intervals will be. The prediction intervals will be on the y variables only, like this. They'll get narrower towards the middle of the data and wider towards the edges of the data. How are we going to calculate these prediction intervals? At a given x value, y is going to be between the predicted y value plus some margin of error and the predicted value minus some margin of error. The margin of error will depend upon the x value that we've chosen. In particular, the margin of error will have a critical t with alpha split between the two tails, as usual, times a standard error for the estimate, and then a third factor, the square root of 1 plus 1 over the number of data points plus x minus x bar squared over SSX. This is what makes the intervals wider the farther you are from the middle of the data. If x equals x bar, this term will be 0. And so you'll have just the square root of 1 plus 1 over n when x is at the mean x value. There are two things left to define: the standard error for the estimate and SSX. Here we have the square root. It's the sum of y minus y hat squared divided by n minus 2 with the degrees of freedom of n minus 2. SSX, on the other hand, is the sum of the x squareds minus the sum of the x's squared divided by the number of data points. It's not hard to see that this is also the sum of the x squareds minus n times x bar squared. So either of these two will work. This gives us the margin of error for the prediction interval. For our first example, we're going to use the exact same data for galaxies that we used before. Give a 90% prediction interval for recessional velocity of a galaxy that is 25 megaparsecs away. I've taken the liberty of entering the data into two lists. And so we have the distances in megaparsecs and the recessional velocities in kilometers per second. So I'll exit out of this. Now there's a real easy way of calculating the least squares line of best fit. You go to Calc, and you can see there's linear regression ax plus b and also linear regression a plus bx. Well, some of the other algorithms use a plus bx, so we'll just use that one here. You're allowed to enter the lists and then calculate. Notice it uses y equals a plus bx. B is the slope. I'll write it as m here. So the slope is 69.09. I'll round it there. And the intercept is 19.80. We can predict values for y using mx plus b. So if x is equal to 25, the predicted y value, if x is the distance of 25 megaparsecs, the recessional velocity will be this 69.09 times 25 plus 19.80. And so I'll type this into the calculator. We'll crunch these numbers on my calculator. I'll type 69.09 times 25 plus 19.8. We have a predicted recessional velocity of 1,747 kilometers per second. This is a point estimate. It would be better to have a prediction interval that has some confidence level. I have to be honest with you, there's no real easy way to do this. Our prediction interval formulas had a standard error for the estimate, a critical t, we had this SSX thing, and this big old square root to calculate. So we have a number of different formulas that we can use. The degrees of freedom is the number of data points minus 2. We have SE, the standard error for the estimate, and unfortunately, the only thing that your calculator will calculate is this standard error for the estimate. We can also get these critical t's by using a t inverse. So these two things we can get. The SSX, we're just going to have to do that on our own. Now, how do we get the standard error for the estimate and the critical t's? You'll recall for the critical t's, we can use second distribution and then inverse t. If we want, say, a 95% confidence level, we'll leave 2.5% in each tail. So I'll have 0.975. That leaves 2.5% in the right tail. Remember, this inverse t only calculates accumulated areas from negative infinity up to this particular area. The degrees of freedom that we'll need is 2 less than the sample points. So that's going to be 13. So the t critical that we need is 2.160. 2.1604 if we round it to the fourth decimal place here. That's the critical t that we will need. We also need the standard error for the estimate. Fortunately, the calculator will calculate this for us. I just have to show you how to do that. Go to Stat, then Tests this time. Going up from the bottom, we have something called a linear regression t-test. It will use y equals a plus bx. It will give you the a and the b values just as before, but it gives you this s. The s that it gives you is exactly the standard error for the estimate that we need. I'll round it to 4 decimal places here, 175.1547. But we still don't have the SSX. A simple formula for that is to add the squares of x minus x bar. X bar is the mean of the x values. How can we get the mean of the x values? Well, we can get that from our one variable stats using list 1. That's where I put my x values. So x bar is 21.5067, rounding it to 4 decimal places. 21.5067. I can calculate the differences of x values minus the mean squared on the calculator. But the rest of this calculation is probably easier to do in a spreadsheet. And so that's what we're going to do. Very unfortunately, most of the rest of this, there's nothing here. There's no test. There's the linear regression t-interval. That gives you a confidence interval for the slope, which is not what you want. Linear regression t-test, that's a t-test for the correlation coefficient. And so there are elements of what we need here, but nothing has everything that we need. And so we may be better off just using a spreadsheet for the rest of this. Microsoft Excel has more features for linear regression than we have here in OpenOffice, but even Excel doesn't have everything that we need for easily calculating these limits, for easily calculating the endpoints of the prediction interval. We'll need a lower limit and an upper limit for these things. Let's calculate the x bar, the mean of the x's. You can do that easily just by typing in average. This is our x bar. So I'll label that as x bar. These are our y values. We have most of what we need from the calculator. What we need is that SSX. How do we get the SSX? Well, here's how. I'm going to calculate the x minus x bar squared by doing the following. I'll get my x minus my x bar. Now this one has to be, it must be surrounded by dollar signs to make it an absolute reference. So I have this x minus x bar for each and every single one of our x values. What I need is the sum of all of those. That is SSX. Once we have this SSX, we need to calculate that last factor. Let's see, I'll type it right here. This last factor, it was the square root of 1 plus 1 divided by n. N was 15. Plus, it was x. In this case, the x value is the x value that we're trying to get a prediction for, and that was 25. Minus x bar, quantity squared, divided by this SSX. So that's the factor that we needed. We can type everything in now if we wish. There's the lower limit and the upper limit on the confidence interval. Let me write down what our t critical was and our standard error for the estimate. The t critical was 2.1604, and the standard error for the estimate was 175.1547. Let's see, what was our y hat? Y hat was 1747. So this will be y hat minus the t critical times the standard error for the estimate times this final factor. The upper limit will be the y hat plus the t crit times the standard error for the estimate times this final factor. This gives us a 95% confidence interval for the prediction value. The prediction value is 1747, but we're 95% sure that the recessional velocity will be somewhere between 1355 and 2139. So, once again, what did we have to do? We needed to get this average. We had to get these values x minus x bar quantities squared. We had to use the dollar signs in here. We had to add all of those up. Once we did that, we could get this factor, square root of 1 plus 1 over n plus x minus x bar squared divided by SSX. We had to have the critical t, and we could have done that on the computer as well. The standard error for the estimate could have been done on the computer, I suppose, but that would require a little more computation. It's probably easiest to get the standard error for the estimate from the calculator. And we got the predicted y value from our mx plus b. Remember, we had the slope, and we can get the slopes here and the intercept using slope. You enter the y values first, and then you enter the corresponding x values. And for the intercept, the word is intercept. You enter the y's, and then you enter the x's. We could get the y hat from this by just taking the slope times 25 plus the intercept, just like that. it's only fair to show you that we could have gotten the least squares line of best fit from a chart. You can select your data and insert a chart. Of course, we want an XY scatter plot. You can see how the distances and recessional velocities look quite linear. Right-click on one of these data points. We want to insert a trend line. And we don't want logarithmic exponential power, and we do want to show an equation. It gives us the slope-intercept form of the line. This is exactly what we needed to make the predicted value. Aha, so there's that advantage to the spreadsheet as well. While the data analysis tools for Microsoft Excel will do multiple regression and linear regression, there is a tool here in OpenOffice that will do some of that as well. It's called LineEst. LineEst. You have to enter the Y values and then the X values. We're always going to use true and true, which is 1 and 1. Now you don't just hit enter with this function. This function requires that you press Control, Shift, and then enter. Notice that this gives you the slope of the least squares line of best fit, the intercept. The next row gives you the standard deviations for the X and the Y variables. So maybe I should write this down, the slope and then the intercept, standard deviation on the X, standard deviation on the Y. The next row gives you R squared, which is the coefficient of determination. It's a lowercase r, just like that. Notice that it's giving us the standard error for the estimate next, which is really nice. We had to work real hard to get that standard error for the estimate before, and it's giving it to us automatically. It then gives you an F statistic and a number of degrees of freedom. And then it gives you the sum of the squares for the regression and the sum of the squares for the residuals. And so this is the entire table. We're using M, B, and the standard error for the estimate. We'll still have to calculate the critical T and this extra factor so that we can get the margin of error.
In our next example, we'll use a table of 40 paired shoe print lengths versus heights. Given a particular shoe print length, perhaps that's been found in the dirt, can we predict how high that person is, how tall that person is? First of all, given the data, we find sufficient evidence to support the claim of a linear relationship. The regression line is y hat equals 3.22x plus 80.9. So we'll be using this for making predictions. If the individual's shoe print was
29.0 centimeters, a prediction interval for the person's height. We'll be able to say the person's height lies within some particular interval. I've obtained from the website for the textbook a bunch of data. We have male versus female and the sex, ages, foot length, shoe print size, shoe print size, and height of the individual. I just want to do a prediction interval for shoe print size versus height. So I'll take these and copy them to a new and separate spreadsheet. So I'll take that one and that one. And there's my data. We can select those two sheets of data. By the way, there are 40 rows here. It goes down to 41, but the first row were the labels. If we want to, we can insert a chart. We'll of course want an XY scatter plot here. And it looks like the data can be thought of as being more or less linear. In fact, we can insert a trend line and show the equation, giving us the slope and the intercept. So there's our line, slope and intercept form of this line. We can use this equation to then make predictions for various values. In particular, we want to know the height of a person whose shoe print is 29.0. So we'll use x equals 29.0 given this slope and intercept. Actually, I'm going to start by finding the slope again using our slope formula. That's going to be over here in second column. Oops, went too far. And then you have to enter the x values after that. For the intercept, it's the same kind of thing. Enter the y values first, and then the x values. So if x is 29.0, what is the y hat? It should be m times x plus b. So we're predicting that the particular individual with a 29 centimeter shoe print size is about 174 centimeters tall. But we would do better to have a confidence interval. So we need a t-critical. That's done a little bit differently on the spreadsheet OpenOffice. It uses t inverse. The number is always for two tails here. So if we're looking for a, let's see, how much confidence do we want? Let's say 95% confidence interval. Then we want 0.05. Then we need the degrees of freedom, which is 2 less than the number of data points. In this case, that's 39. So our critical t is 2.023, it looks like. So we have the critical t. We need the standard error for the estimate. And so the way to get that, we need to get y hats for each of these values, predicted values. So that's going to be m, which we'll use as an absolute reference, times the x plus the b, which is also going to be used as an absolute reference. We need to paste this down, and so we'll drag this down. The standard error for the estimate is the sum of the y minus y squared divided by n minus 2, all under a radical. So I need more room for calculation here. I'm going to insert a column. And I'm going to calculate y minus y hats squareds. These are the y's. I need a parenthesis first. Y minus y hat squared. And I'll paste that down. I'm going to calculate the standard error for the estimate now. How do you do that? It's the square root of the sum of all these differences that we just calculated divided by n minus 2, which is, let me go back up so you can see the formula before I close this out. Square root of the sum of those predicted differences divided by, oops, not 25. We have 40 data values, so it'll be 38. That's the standard error for the estimate. We need that additional factor. For that, we need the SSX. And for that, we need the mean x. X bar. That's the average of the x values. So to calculate the SSX, we need yet one more column. I'll calculate it here. These are going to be the x values minus these x bars, which has to be an absolute reference. I'll write this as x minus x bar squared. Yep, we squared that. We'll need to pull that formula down. The sum of all of those is the SSX. The sum of all of those values. We're ready for that factor. Which is the square root of 1 plus 1 divided by the total number of data values, which in this case is 40, plus the predicted x value, we wanted 29 centimeters, minus the x bar, and that gets squared. Oops. Divided by the SSX, and that gives us that extra factor. The margin for error is the t-critical times the standard error for the estimate times this additional factor. The lower limit and the upper limit now can be calculated. The lower limit is going to be our y hat minus the margin of error, and the upper limit will be y hat plus the margin of error. So these values here give us the endpoints of a 95% confidence interval. Lower value of 162 centimeters, higher value of 186 centimeters. Now, that was quite a computation, but it can be done, and you just have to follow what we have done here.
It can be shown that for R, which is the correlation coefficient, that R squared is the sum of y minus y hat squareds divided by the sum of y minus y bar squareds. We call this the explained variation over the total variation. We'll make a definition. R squared is the coefficient of determination. And in particular, R squared is the proportion of the variation in y that is explained by a linear relationship. So you can see on the bottom here, if we have data like this, here's your x bar, y bar. Y minus y bar is just the distance between all of the y's and this level y bar. Some of them may be negative, some of them may be positive. We'll take those differences and square them and add them up and define that to be the total variation in the y's. If y were perfectly constant, the total variation would be 0. We're assuming that isn't the case here. We're dividing by the thing. On the other hand, y minus y hat is a much smaller difference for each of these, the distance to the line of best fit. So if you add up those squares, you get the variation off of the line of best fit divided by the variation off of the mean y value. So you get a proportion of the variation of the y's that comes from the linear relationship. This is how far it's off of that linear divided by how far it's off of the actual mean. Here's a funny example. Over a period of years, the number of people in a certain town who attended church was correlated to
the number of people who were incarcerated. It was found that the correlation coefficient was 0.90. So, does this mean that the more people who attend church, the more people will have arrested for some reason or another? Correlation of 0.90? Or is there another underlying factor that it can explain both? In this case, the correlation is explained by increasing population. As the population goes up, the church numbers go up, and those incarcerated also goes up. So, even though there may be a very strong linear relationship, it has nothing to do with causality. It doesn't mean churches spread crime at all. There's no causal relationship. In the shoe print height example, R was 0.813, and that gives a coefficient of determination of 0.661. That means that 66.1% of the variation in height can be explained by shoe print length. The other 33.9% cannot be explained by shoe print length, but perhaps some other variable. We will now discuss multiple regression. As we've been implying, there could be multiple variables that can be used to predict a single variable. This will describe a relationship involving multiple independent variables. In this case, we'll have a predicted value y hat. We'll have a b0, a b1 x1, b2 x2, b sub k, x sub k. We may have k different independent variables that we can use then to predict this other variable, y. As an example of these different variables, we could have sex, age, foot length, shoe print size, and shoe size as predictors of height. We have a whole bunch of different independent variables, each of which does affect a prediction about a person's height. K is the number of predictor variables y hat is the predicted variable, and we'll assume that we have n data points. This y hat is the predicted value from the sample. From the population, we're going to use Greek letters for our parameters. These are statistics, and these are going to be parameters. Beta naught, beta 1 x1, beta 2 x2, to beta sub k xk. The regression equation has a standard error that is often denoted by epsilon. It is assumed that these are normally distributed, with a mean of 0 and standard deviation of sigma. And also that standard errors are independent. Example. I've copied some of the data about age, foot length, shoe print, shoe size, and height. It may not be advisable to predict height from all of these variables, but let's see if we can do the multiple regression for this data anyway. Let me leave ourselves a little room by scrolling over to the right a little bit. We're going to use linest. And first we select the y values. Those are the heights. We then need to select all of those x values. And by that, I mean, let's select all of them. All of those. And then 1 and then 1. So let's see what we have entered here. This is the command. We have to press Control Shift, and while we're holding down Control and Shift, we press Enter. And it gives us this whole multiple regression. This is the B0, the constant term in the linear regression, the multilinear regression. This is B1, B2, B3, and B4. It puts them in backwards order. Yes, there's nothing we can do about that. Backwards order. Okay, so we have B0, B1, and it's making them capitals. They should be lowercases, B2, B3, and B4. Then you have the respective standard deviations. So the second line is the various standard deviations. We'll have the coefficient of determination in the standard area for the estimate, F statistic, degrees of freedom, and sum of squares of various errors on the last line. So again, there are elements of this that we can use for our multiple regression. This will be the constant term. We'll have x1 times b1 plus x2 times b2 plus x3 times b3 plus x4 times b4. You plug in different values for these x's plus this constant term, and it outputs an estimate for the height. Let's see, note that what we're doing then is we have the ability to input a shoe size, a shoe print size, a foot length, and an age. This will be times B1. The number here that we input for foot length will be multiplied by B2, shoe print size times B3, shoe size times B4. Add all that to B0,
and you get an estimate for the height. Let's do a quick example. Let's suppose we have values for the x4, x3, it's awkward that they make these go backwards, but they do. And then we'll, let's see, x4 was shoe size. Let's suppose someone has shoe size of 10. Let's see, what were the other variables? Shoe size, shoe print size, foot length, and age. Shoe print size, I don't know, 29.1, foot length 28.1, and age, let's suppose the person is 25 years old. What we can do is we can estimate the height of the individual by taking 25 times this coefficient at the top plus 28.1 times the coefficient at the top plus 29.1 times the coefficient at the top plus 10 times the coefficient at the top plus the constant term, and that gives an estimate for the height of the individual, and that's right here. We multiplied all of these together, added the constant term, and that gave us an estimate for the height of the individual in centimeters.
In the multiple regression case, we have an adjusted coefficient of determination. This has the value of 1 minus the quantity n minus 1 over n minus k plus 1, all times 1 minus r squared. N is the sample size, and k is the number of predictor variables. You may be tempted to think that the more variables you include in a model, the better the predictions will be, but that's not always the case. Sometimes it is best to exclude certain predictor variables. You will use common sense as to which variables should be included, which should not. We'll consider the p-value, and lastly, we'll consider variables with high R squared and exclude all but a few. A dichotomous variable is a variable that can have only two values. In this case, we assign those values either to be 0 or 1. One of the values we'll say corresponds to 0, the other one corresponds to 1, and we'll use that in our multiple regression. Such a variable is called a dummy variable. When this new variable that we assigned is called a dummy variable.